Okay, so let's see. Starting with Nicola at the end. What letter represents the melting of the solid? B is correct. Jeff, what represents the boiling of the liquid? D is correct. Which letter represents the region where the kinetic energy is being changed? A, C, and E. Alright? So all three regions, because the definition of temperature is average kinetic energy. Is that right? They're one and the same. Which regions represent where potential energy is being changed? B and D is correct. So it's increasing going in this direction. It's B and D. The letter which represents where the solid is being warmed, Sydney, is correct. All right. Let's come down. The range where the liquid is being warmed, C is correct. The range where the gas is being warmed, Jimmy, E is correct. What is the melting point of the substance? 0 degrees Celsius. What is the boiling point of the substance? 50 degrees Celsius. What is the freezing point of the substance? It's 0 again. What represents the condensation point? 50 degrees Celsius. What happens to kinetic energy during a phase change? Lydia? Yeah? When it's changing phase, as it's melting or it's boiling, phase change means change of state, right? Whereas when a solid is becoming a liquid or a liquid is becoming a gas, it's called change of state or phase change. What happens to kinetic energy? So kinetic energy is this line. Temperature is the kinetic energy. Is that right? So what happens to kinetic energy during a phase change? Do you see the temperature increasing in this flat line or this flat line? Is the temperature going up or down? It stays constant, right? So you have to say the kinetic energy stays constant. But what happens to potential energy though? It increases, all right? Stays constant, whereas your potential energy increases. Right? Yes, Sydney. Okay, what is the letter there? Letter is B. Is that condensation? So it is D. That is correct. Okay. Okay. So we all understand freezing cooling curve. Is that right? Heating cooling curve. Now, let's go to the next page. So when you have a substance, all right, a substance can go from a solid state to a gas state. Is that right? Now we have learned that there are three different equations that we use. We use enthalpy of fusion when it's undergoing melting. We use enthalpy times the enthalpy of vaporization if it's changing into a gas. And then we have the equation mCp delta T whenever there is a temperature change. Is that right? Now, we have three regions in the graph. Along the slopes, it's just a solid state, or it's just a liquid state, or it's just a gas state. Is that right? Along the slopes, the state of the substance is a single state. Is that right? So the equation that you use when a solid is being heated, a liquid is being heated, or a gas is being heated is Q equals M times Cp times delta T. So along the slopes, the amount of heat energy that is required to heat a substance, a liquid or a gas is Q equals M times Cp times delta T. But you have to watch out for the Cp. The specific heat of the solid is different from the specific heat of a liquid, is different from the specific heat of a gas. All right? So if you are given information in the form of a table, when the solid is heating, you will choose which one? The specific heat of the solid. Is that right? If it's a liquid, you should know to choose that for a liquid. Is that understood? Now, along the flat line, here it is melting, going in this direction. Is that right? Solid becoming a liquid is melting, so you will use your enthalpy of fusion times mass. There is no change in temperature. Is that right? And along this line, you will use Q equals M times enthalpy of vaporization, because the liquid is becoming a gas. Say you have a substance that is at minus 20 degrees Celsius. Okay? And you're heating the substance all the way to 120 degrees Celsius. Are you with me? You're heating it from minus 20 to 120. What is the heat change involved during such a process? It's a physical process, right? So if you were to do the calculations, here is how you would do the calculation. So let's look at this one. This is your step 1. All right? This is your step 1. And in step 1, it's going from minus 20 to 0. Is everybody with me? It's going from minus 20 to 0. So what is happening? The solid is being heated. Do you agree? So the equation I will use is Q equals M times Cp times delta T. Is that right? And now the mass of my substance is 52 grams times the specific heat is given 2.06 joules over grams degree Celsius times the change in temperature. How do you calculate change in temperature? It's always T final minus T initial. We cannot forget that. Is that right? My T final is what temperature? Is 0. What is my initial temperature? Negative 20. So my change in temperature is actually 0 minus of minus 20 degrees Celsius. Would you guys agree? So what is minus of minus 20? Plus 20. Therefore, it's times 20 degrees Celsius. Are we good? Are we good? So if you multiply, have you all done this already? No? Okay. So let's see. If I multiply 52 times 2.06 times 20, this calculator doesn't show things properly. What do you get? Are you doing the math, or am I the only person doing the math? I don't like it if the teacher works harder than the student. My student should be telling me the answer. What is the answer? 2142. For now, I'm not going to round. I will round at the end. Okay? 2142 joules. Is everybody good? Okay? Now, can I pause this for a moment and it started boiling? Can I show you the graph again? Alright, it's now boiling. So let's go back to that data collection there. And this is now too big, so I'm going to reduce the size. Do you see it started becoming flat? So here is the 0 to a 200. It started out below 0. It gradually increased in temperature. Now it's becoming flat. Do you see that? Even though water is boiling, and heat is being provided, will the temperature change? You will really be able to see the nice flat line here. We'll come back to it a little bit later. All right? So during a change of phase, does the temperature change? So what is the heat energy being used for? What is it being used for? Conversion. To do what exactly is it converting? It is converting a liquid into a gas. So what exactly is it doing within the system? It's breaking bonds. breaking bonds, is it endo or exo? Endo. It requires heat. Otherwise, the water cannot become steam. Is that right? It requires heat energy, and all the heat energy is being used to break those bonds between water molecules. What kind of bonds exist in water molecules? We did this in biology. Hydrogen bonds. It's breaking those hydrogen bonds between the water molecules. And now, if I take water, so here is water. Water is a Mickey Mouse, correct? 2 hydrogens and 1 oxygen. And this is my hydrogen bond between 2 water molecules. Is that right? The blue bond is my hydrogen bond. All right? This is, each one is my H2O molecule. Is that right? Yeah. This is H2O liquid. All right? When it becomes H2O gas, when I say it's breaking bonds, is it making it this way? Is it like breaking off its ears? Or is the water molecule still this, but then they are separated from each other? There is one water molecule that's flying away, another one that's flying away. I'm saying, wee, what is going on? What is going on? Each water molecule is flying away. Is that right? When you're providing heat energy, it cannot break its ears. That bond is not being broken. The heat energy is not enough to break its ears. Does that make sense? They only are getting separated from each other and they're flying off. Do you see them flying off? Do you see that? Do you understand the process? The hydrogen bond is being broken. Do we get it? All right. Let's go back. It's flat. Do you see the nice flat line? Are you able to see that? Do you understand the process? Yes, sir.
So how do we like measure what the specific heat of gas? Doesn't it expand even more?
So I can do heat loss, heat gain type of formula setup, and I can work it out. All right. Exactly for a gas, how do we do it? I would have to sit down and think. I haven't done a lab where we actually find the specific heat of a gas. It's more easier to deal with solids, right? Or a liquid, but I haven't done it with a gas. So yeah, there are ways they find that out. All right. Heat loss, heat gain is the principle used. Okay. So going back to my formula again, I will switch it off in a little bit. Okay. You go, if you see the water completely draining off, let me know. Sometimes I'll get caught in the class and not watch it. Okay, so now, so I calculated my heat change for my solid to go from minus 20 to 0. What is the next step? The solid is melting. Is that right? Step 2, the solid is melting. So what is my equation? Q equals M times heat of fusion. Fusion is the fancy word for melting, correct? So the amount is 52.0 grams times, what is my heat of fusion? 334 joules over gram. And what is the answer? One seven 368 joules. All right, we got that. So now it's gone from this point to this point. Is that right? What is the third step? Step 3 is, it's here. Where is it going to? Is it going to the top? Right? Is it going to the top of the curve? So what is the equation I will use? What equation will I use for this slope? Q equals M times Cp of what? Cp of the liquid times change in temperature. So the mass of the substance is 52.0 grams times the specific heat is given 4.18 joules over grams degree Celsius times, what is my final temperature? 100. What is my initial temperature? 0. Final minus initial is 100 minus 0 is a 100 degrees Celsius. So what is my heat? involved in heating up the water? Yes.
21762.
21762 joules. All right. So I am here at this point. What goes on next? This is the stage we are watching here. Is that right? The next stage is the stage we are watching. The liquid is evaporating or boiling. Is that right? So what is my equation I will use? What equation will I use? Did I do it wrong? Is the answer wrong? Everybody's talking to each other. There is something wrong. What is it? Somebody got that? What is the answer?
Oh,
21736. Okay, I like that. They correct each other's work. Good. Now, let's go to step 4. What is my equation? What equation do I use? Q equals M times heat of vaporization, HVAC. So the mass of my substance is 52 grams. My heat of vaporization is 2260 joules over grams. So what is my final answer here? Yes. 118,000 joules. All right. So I am in this stage now. What is my final stage? The gas is being heated up. Is that right? So if I go to my final stage, which is what equation, guys? Q equals M times Cp of what? Cp of the gas times delta T. My mass is 52 grams. My specific heat of the gas is given 2.02 joules over grams degrees Celsius. What was my final temperature? 120. What was my starting temperature? 100. So 120 minus 100 is 20 degrees Celsius. And what is my answer? 101 joules. Okay. So I need to find the total energy, heat energy required to go from minus 20 to 120. Now I have 5 different steps. What am I going to do with all these numbers? Add them all up. All right. So at the end, you just add them all up. So I have my Q final equals 2142 joules plus 17368 joules plus 21736 joules plus 118,000 joules plus 2101 joules. What do you get? What do you get? I made a mistake first period when I added. Kids make mistakes all the time. Yes.
So for number 4, you have 11800.
Uh-huh.
So shouldn't it be 117520?
Okay. I did not round. I don't like to round. 117520. So let's make that 117520. Hey, how are you? Doing well?
Yeah.
Okay. This is okay. You want to stay to the end of class? You were not yet ready for the quiz. All right. So let's see. Where did we get? What is the answer? Anybody? Yes, Tyler. 160,867 joules. All right. So here is how I round. I don't round every step of the way. I round at the end. If I look at the problem, I see most of them are 3 significant digits. All right. 3 sig figs is my least. I'm not looking at this. This is a poorly worded temperature. It should have been negative 20.0. Does that make sense? So I'm going to round to 3 sig figs. So which makes my answer 161,000 joules. Is that pretty good? That's my total amount of heat energy required to change the temperature from a negative 20 to 120. Is that clear? Now, let's go to the next page. All right, let's go to the next page. Now, sometimes you will be given the heating cooling curve. Sometimes you will not be provided the heating cooling curve. All right. How do you draw a heating cooling curve if you're just given a table full of information? Now, before I go to that, I want to switch this off. So my water has become substantially smaller in amount. Do you guys see that? Well, I need to erase this because this blue on top is like really, it's still, well, here is the beginning temperature. So if I scroll down, the temperature, it was melting. So all the heat is going to actually melt the solid. And then it's very interesting that you will see that it's -4. There is a big concept that ice water actually does not freeze at 0. It's more stable at -4. I'm not going to get into all that right now. And then the temperature drastically starts increasing. Do you see that? Do you see those temperature changes? Every number is different from the other. And look at that. At 100, and notice that it's not exactly 100. It's a little more than 100. Maybe towards the end of the year, I can tell you why it's a little more than 100, why it's a little below 0. All right? Impurities in water make it drop or rise. All right? In brief, for now. All right? So look at that. It's still 100 and it'll remain flat. Will continue to remain flat till all the water evaporates, is gone. Okay? Was that cool? Okay. Now, let me switch this one off. Now, let's go back to our calculations. So, here, this is, the data is 0 and 100. Is that right? Say I had not. I'm making up a number here. Okay? I want you to stay with me. Say I'm making up a number here. And I say my melting point is -20 degrees Celsius. Are you with me? And the boiling point of the substance is 30 degrees Celsius, plus 30. All right? So you're asked to, say, do a problem where the substance is changing from -10. Do a problem where the substance is changing from -10 to 10. All right? Find out how much of heat energy do you require to change the substance from -10 to 10. They've given you such a table and they've given you the melting point and the boiling point. As I do, you do. I know you have that graph, but on the side, can you also write these things down so that it's helpful for you to go and process this information at home? All right. So when I'm given a data table, but I'm not given any heating cooling curve, all right, say this is not all provided to me, one of the first things you need to know is to draw a heating cooling curve. Is that right? So how do you draw a heating cooling curve? I need my axis. Is that right? What will I look for? What is the first number I will look for? What is the melting point? The melting point is -20 degrees Celsius. Is that right? So I'm going to plot a point. I'm going to say that is negative 20 degrees Celsius. Everybody good? And I'm going to draw a flat line, indicating that it's melting. During melting, is it flat? Now, I mark my next line, all right, which is my boiling point. Is that right? That is my boiling point. And what is that temperature? 30 degrees Celsius. Now, am I ready to complete my heating cooling curve? Yes or no? Can I draw the three states of matter? Can I draw the three states of matter now? Right? It's the solid, it's the liquid, and that's the gas. And on the flat lines, I know it's melting and it is boiling. Is that right? Now let's look at the temperature change they want me to follow. Where is negative 10? Can I say negative 10 is here? Right? And then it's going to 10. So it has to go through step 1. Is that right? Is this process 1? Is this process 2? And then it is at 10. Is this step 3? So how many heat calculations do I have to perform? 3 different calculations. And then what will I do with those 3 numbers? Add them up. It's not a simple problem. Does that make sense? You actually have to figure out the changes through which it is undergoing. Now, can you try this problem, please? Do it with a pencil. Do it with a pencil. Try the second problem. And there are little things that I would like to teach you before I give you the quiz. So I would like you to try. What did I do? Yes, you are right. I'm wrong. Well, no. It will be negative 20, negative 10. On a number line, negative 20 is a bigger number than negative 10. So if you see a number line color, is this how? Say it's 0. All right? This is 10. This is 20. This is positive 10, positive 20. This is going to be what? Negative 10, negative 20. Negative 10 is a bigger number than negative 20. You don't look at 10, 20 and decide. When it comes to negative numbers, the smaller the number range, the bigger it is. What did I do? Oh yeah, oh yeah, oh yeah, she's right. So negative 10 should be here, right? Which makes it a single step problem, right? Yes, she's right. You're right. You got me there. Okay. Yes, you're right. Okay. That is right. I gave, yeah. Sorry guys, I messed that one up, didn't I? Negative 10 is going to be higher. So negative 10 will be higher. So this will be the only change that's taking place. It'll be a single step problem, right? I did mess it up there. Thank you, Skylar. All right. So try this problem and we'll come back to it. Yes. Yeah, why don't you go in here? Let me actually pause this recording.
Wait, did that record your voice too?
And do the problem. So we are aware that the melting point is still 0 degrees Celsius and the boiling point is still 100 degrees Celsius from the graph. All right. So it is going from 120, which is this point, to a 50, which is this point. Is that right? So how many steps are involved? 1, 2, 3. Is that right? I have to do 3 separate calculations. Correct? Now, my first one is this. And the equation that I need to use is Q equals M times Cp of what? Cp of gas times delta T. The mass of my substance is 10 grams times, I go up to my table, what is the specific heat of my gas? 1.996. So 1.996 times, I have to calculate the change in temperature. And change in temperature is always T final minus T initial. What was my final temperature? 100. What was my initial temperature? 120. 100 minus 120 is negative 20. Alright? Negative 20 degrees Celsius. That's 20, by the way. There is a decimal point there. So if I multiply, can somebody tell me what you got? Negative 399 joules. 0.2. Alright, 0.2 joules. Alright? That's my Q1. Now, for my second step, alright, Q2, I know the liquid is condensing because the gas is becoming a liquid. The process is condensation. It is not evaporation. Is that right? So, it's M times heat of condensation. Well, the heat of condensation is not given. Only the heat of vaporization is given. Do I know that my heat of condensation is the same as my heat of evaporation, but with a negative sign? Numerically, they are the same, but the signs are opposite. So, therefore, it is mass is 10 grams times 2259. This is joules over grams. So the units will cancel, grams will cancel. And what is my answer for the second one? What do you get? Anybody? 22,590 negative joules. Right? There's just one more zero. I don't know why it had to ask. Okay, just add a zero at the end, right? Everybody got that? All right. So the last and final step, Q3, the liquid is cooling down. Is that right? So it's M times Cp of the liquid times delta T. Correct? So my mass is 10 grams. I need to find the specific heat of my liquid, which is 4.184 joules over grams degree Celsius times, I have to watch out for my temperature change. What is my T final? 50 degrees. My T final is 50. What was my T initial? 100. So what is the change in temperature? Negative 50 degrees Celsius. Is that right? So if I multiply, what do I get? What do I get? Negative 2,000, 2,092 joules. And how do I get to my final answer? Q final equals, I add them all up, minus 399.2 plus 22. Well, can I put the negative sign outside? Because everything is negative. Is that right? So I'm just going to add them all up. 22590 plus 2092. And my final answer will be in joules. So if you add them all up, what do you get? 1,
Negative 25,000.
25081. 081. That's a 5, guys. 25081.2 joules. Now, if you look at the problem, the lowest is 3 sig figs throughout. Is that right? The lowest is 3 sig figs, so I'm going to use 3 sig figs minus 25100 joules. Is that right? Did everybody get that? Do you understand the process? So when you're cooling, it is released. Heat released is always negative. Alright? You have to say it's a cooling process. You have to tell me it's an exothermic process. You have to show it through the sign of my final answer. Heat released is, yeah.
Like, kind of doesn't make sense for something to be released negative because, like, it's like saying distance is negative.
The way the question is worded, it says the amount, but a quantity shouldn't really be negative. It's like saying that I'm holding negative.
So how should I have worded it, David? Well, my English is
What
not
is
that
the
fabulous.
change?
Huh?
What is the change?
What is the change? All right, I will make note of it. All right. So the question says here, calculate the amount of heat released. Calculate the change in heat. Can I say that? Change in heat. I don't want to give it away to the kids, but in a way I'm giving it out that it's being released and it's exothermic. So there is one more thing I would like to teach my kids. All right, I do not teach this at this level. It's not required. But if you go into AP Chem, you will learn it. I think you learned it as a part of your introductory, taking little vocab words from your heat unit. You always look at heat changes with respect to the system and the surrounding. Did you know that? I don't know if you read the textbook. You have what is known as the system and you have what is known as the surrounding. All right? So when we say exothermic, it feels hot. It's actually heat is being released to the surrounding. Is that right? We always look at heat changes in the surrounding. When we say it is cold, heat is going from the surrounding into the system. When we talk of an exothermic or an endothermic reaction, what are we considering in our reaction? We're only considering the surrounding. We never actually talk about the system. Some of the reactions may become confusing, but you actually learn it in the context of system and surroundings, it will become much more clear. All right? So you will get tripped up on a little example because I don't teach that concept at this time. But remember, exothermic, heat should be negative. Endothermic, it should be positive. Is that clear? All right? Let me stop recording my lecture now. And I'm going to post.